Well, in fact, when we measured the room, and it was about 2 seconds, it's a really big room, and it did roll off at the low end. So where was the low frequency absorption? There's no absorption at all, it's all wood. Well, it turns out the wood is very thin. There's no insulation in this building. It's a cabin. It's a big cabin, but it's a cabin. No heating. It didn't serve, it didn't work in the winter. So the walls were actually quite thin. And so some of the sound is just going out of the building. Okay, and that's how it's absorbing, because if sound leaves the building, it's a kind of absorber. So that, when we designed and tried to make this, convert this into a studio, the goal was, how do we keep that low frequency characteristic, but still put a shell around the outside of the building, because that's exactly what we had to do. Pardon me? Absolutely, that was the huge issue with this studio, and the owner had not thought about that. Good point. The owner had said, well, we're on top of a mountain, what do we need isolation for? I said, have you ever been here in a rainstorm? Have you ever been here in a windstorm? It's actually quite noisy. In fact, it was very noisy inside. I mean, noisy enough that it would bother microphones. And so we basically built the building around the building to look exactly like the building. But, I mean, literally, we built this giant condom, okay, around the building. We'll use a different word in the video, right? I don't know how to describe it any other way. It was, I mean, easier said than done for about $250,000 worth of building. But when we did it, we left a 6-inch airspace. We actually furred the building out 6 inches so that the skin on the inside of the space still was presented to the space. Sound still could get out and vent itself in this kind of air chamber. If we hadn't have done that, if we had taken this skin and slapped it right up against the wood, we would now make a stiff boundary, which is the backbone of most recording studios. Most recording studios that require isolation do it with stiff boundaries. Basically room within room construction, of which the boundaries are stiff. 3 layers of sheetrock, masonry, sand-filled, sheetrock, vinyl, plywood. I mean, different combinations of stuff, but when you add them up, it gets stiff. Masonry is stiff. This is a stiff surface. Low frequency energy is hitting the surface, and it is coming back into the room. Mid and high frequency energy is always going to get absorbed. Air absorbs 8,000 hertz. People absorb mid and high frequency energy. Banners, it's not hard to absorb mid and highs, but it's very hard to absorb 60 hertz or 80 hertz. That's not so easy to absorb. You just don't do that with some foam. You need either a lot of air, or you need something that's membranic, something that moves like a membrane. Okay? In this case, the entire room was membranic. So when we left that airspace, we were able to just about keep the same characteristic RT. And around this room, we were thinking of putting a control room here. Finally, we just added a control room building right to the outside of this, put a little studio between it and this studio, which also works as a passage, salvaged this room with a complete new inner wall, and basically created this studio. That's that little sunroom. So we're always going to have studios like this, extraordinary destination kind of studios. This is about a $5 million exercise 8 years ago. Big SSL, you can see from the picture here, et cetera, et cetera. But we're not going to have a lot of these, but we can learn from these. We can learn a lot from these kinds of studios. Yeah?
So how did you know that 6-inch will be enough?
Well, we did calculations. It's actually pretty easy. You can do it mathematically, but actually you can do it really easy now by modeling in some relatively inexpensive, relatively meaning $5,000, relatively inexpensive desktop, runs on a PC. I mean, you may have to hit a button and go to lunch and come back for the processing, but you don't need a Cray computer, where we can model the absorption of an assembly, and we can model the internal room response of a volume by touching every single surface and giving it a characteristic. So first we have to get the characteristic of the assembly, and then we have to put it into a 3D model. Okay, there are several programs that do that. WinFlag is one of them. Bastion is another one, mostly from Europe, ironically. Cat Acoustics from a Norwegian company or German company. We use Cat, and the guys in my Swiss office do most of that. It's not Best Buy stuff, It's not, it's not Photoshop, but it's not rocket science. It's pretty amazing, and this is all in the last 10 years. That's what we're going to see a little demo of. Okay, and that's exactly how we did this. okay? So this is very exciting, and when you have a big project like this, of course, we get to play. The fees are a little bigger, and you get to play with the toys and get a very high learning curve. Okay, so, and we're still going to have a need for bigger studios. Now, here's a commercial studio, very successful. This is a studio for electronic arts, and this is, the headline here is Special Purpose-Built Studios. This is not a studio for hire. This is not the Hit Factory. This is not the record plant. It's not even Electric Lady. The studio's not for rent. This is a studio, and actually there's a lot of studios. 1, 2, 3, some post-production rooms. This is a 25,000 square foot audio complex inside this giant building. It's one of their 2 headquarters. This one's in Vancouver, just for the gaming industry, just to make the gaming music. And we all know there's a lot of music in games. The gaming industry is much bigger than the film industry. Everybody should know that. You know it already. So they need a very interesting studio. And look at the isolation between these 2 rooms. Whoops, there goes the laser pointer. And there it is. Why would we put 2 studios next to each other? Because we ran out of space. And when the idea would be to maybe put a corridor between them or a storage closet or something, but we ran out of space, so we have to put a very robust wall there for a lot of very high STC. Let's study that one little studio in more depth. For our office, this was the first studio where we had a full-size 5.1 surround sound system. Even before they were releasing their games in surround, they were tracking everything, and they were producing everything in surround and archiving it. Electronic Arts recognized that surround would be a big deal in the gaming industry. And very interesting room, pretty typical, small console, producer's desk behind it. Basically, and we do this a lot, get the room designed, get the room modeled, get it to work, position it in the space so that the doors work and the sight lines work. Here's a little how do we design a studio 101, not even 101, 0.00101, okay? And then in general, if you get those things to work, the space that's left over is the studio. You can almost get any space to work as a studio if you have enough space. Obviously, if you need to put 30 musicians in a room, you can't have a 10 by 18 room. But the nice thing about this is just with some angles and whatnot, the space itself is already taking on a kind of an interesting acoustic shape. It's already comfortable. Even before we put anything in the room, there were certainly no parallel walls, no flutter echoes, had a kind of excitement to it. Try to stay away from squares. Try and stay away from cubes. Try and stay away from primary dimensions being the same. Why? Because the eigentones, aka standing waves, will have mode pileups that are exactly the same. So you'll have buildups and you'll have voids, depending on whether you're in a null or whether you're in a quarter wavelength position. So try and get rough shapes that are non-cubic or non-square, okay, and that allow for the distribution of modes to be as equal as possible. We now have some math that allows us to do it, and we have our own little software programs that we can see which modes are being piled up on, and when we see we have problems, we can then try to squash the modes, okay? So that already you can see that this is pretty comfortable. No cube going on here. Nice sight line into this vocal booth, and that window is symmetrical to this symmetrical. You're going to see a lot of control rooms. You've already seen a few floor plans, and you will see none that are not symmetrical, at least for the first half of every control room. I can present no argument for non-symmetry in a control room. There is no argument for non-symmetry. There's only arguments for symmetry.